and normal lines. Let's talk about tangent planes. Think about the following surface, z equal to 16 minus x squared minus y squared. What kind of graph would this be? Well, in 3 dimensions, one equation will give you some type of surface. And our goal firsthand is to imagine what kind of surface this is. Let's try that. If you have the xy trace of this, xy trace is setting z equal to 0, and that would mean 0 is equal to 16 minus x squared minus y squared. What kind of curve is this? It's a circular radius 4, because if you move this to the other side, you get x squared plus y squared equal to 4 squared. 16 is 4 squared, right? So this is a circle of radius 4. That's the xy trace. Now, what about yz trace? Yz trace means you're setting x equal to 0. If you set x equal to 0, you get z equal to 16 minus y squared. And that's here's 16. That's the graph. It's an upside down parabola whose z-intercept is 16 if you set y as 0. And if you set z equal to 0 and solve for this, you get y equal to 4 and negative 4. So it's this parabola. Now if you look for xz trace, that's setting y as 0, and it's the same story. Z equal to 16 minus x squared, that's an upside down parabola just like this. So here's what you have. We have some kind of surface, and if you cut it using the xy plane, you get some kind of circle. If you cut it using the yz plane this way, you get this parabola. You cut it this way, you get another parabola. So putting all these together, you can kind of see that the shape looks like the following. It's like upside down parabola in all directions, but if you cut it horizontally, you get this parabola. What is this thing called? Paraboloid, right? It's a paraboloid. And if I draw in the axis, it's like this. So if this is x, that's y, and that's z. There's 16, and it's 4 and 4. That's the type of surface that we have. Now, what we want to do today is to come up with the equation of a tangent line at a certain point on the surface. So suppose your x-coordinate is 2 and y-coordinate is 1. So it's 2 comma 1 comma something. And then what's the z-coordinate of this point? If the x-coordinate of this point is 2 and y-coordinate of this point is 1, what's the z-coordinate?
11.
How did you get 11?
You plug it into the...
Yeah, because the surface is given by this equation, and therefore if x is 2 and y is 1, you just plug it in here, and you get the value of z as 11, right? So 11 is the z-coordinate of this point. What I want to do is to figure out the equation of the tangent plane. So we're looking for this plane that's tangent to the surface at this one point. So let's recall the equation of a plane. For equation of to write an equation of a plane, what two things do you need? You need a point, okay? And then you need what? You don't want to say line.
A vector?
A vector. What kind of vector?
Normal. A unit?
You need a normal vector. Normal vector. That's what you need. Okay? You need a vector that's normal to this plane. We already have this point. It has to pass through this point. But we need a vector that's normal to this plane, which means you need a vector that's normal to the surface at this point. Got that? Okay. So that's all we need. Once we know the vector that's normal to this point, then we would be able to write down the equation of this plane. Okay. Now, how would you get a vector that's normal to this surface? Any ideas?
Cross product.
Okay, that's a good one, but the problem is we don't have two vectors to play with here. Usually if you had two vectors that lie inside the plane, you can just do the cross product to get the normal vector. But the thing is, we're only given the surface. We have no idea what this plane is, so it's hard to figure out what vectors would lie inside this plane.
Can't you derive that equation and plug in the number?
Eventually, you will be differentiating. Of course, you would need to differentiate in order to get tangent of anything, right?
Would you use the gradient?
You would use the gradient. Now, what property of gradient are we using here? If we are to use the gradient to find the normal vector, what property are we using?
First one.
The property that the gradient is perpendicular to what?
The level curve.
The level curves, or in 3D,
Lay.
level
Surfaces.
level surfaces. Okay, so that's what we're going to use. Okay. See, level curves really don't fit what we need. Okay, we need something that's perpendicular to the surface, not the curves. Okay, so we need to think of this given surface as a level surface of some function, and once we are able to do that, then we can take the gradient of that function, and that will provide us the normal vector we need. Okay? So here's what we're going to do. And this is actually the usual plan for any kind of given function. So let me write it here. The standard way that we will approach this problem of tangent planes is to do the following. Suppose we're given a surface z equal to f of x comma y. Now the problem is, if you just say f of x comma y equals to constant, that's a level curve in 2D, not level surface. So what you do is you would change this into the format f of x comma y minus z equal to 0, and then you realize that this is a level surface because, first of all, if you define this much as a function f, capital F x y z, if I define capital F x y z as f of x comma y minus z, I can say this is a function of three variables because it's at x, y, and z, right? That's why I can call it as another function x, y, z. And once you define it like this, then this equation that we have really looks like a function equal to a constant. Really? Isn't that right? So what's a level curve or a level surface? If you're given a function, you set that function equal to a constant. In 2D context, that gives a curve, so that's called a level curve. In 3D context, if you have a function of three variables and you set it equal to a number, that gives you a surface in 3D, so you call that a level surface. And by setting f of x, y, z equal to 0, this is equivalent to the first given surface, right? Because if it's if x, y, z is f of x, y minus z, saying this equal to 0 is equivalent to this one. And therefore, we know that the gradient of this capital F is perpendicular to the surface given by surface f x, y, z equal to 0. Okay. That's what we need. The gradient of f must be perpendicular to the surface f of x, y, z equal to 0. Okay. So let's use that here. What do? We, according to this prescription here, we need to define capital F x, y, z as the small function, this function here, this function, 16 minus x squared minus y squared minus what? What's the prescription for
Minus z.
minus z? You have to subtract z. Okay. Then f of x, y, z equal to 0 really means 16 minus x squared minus y squared minus z equal to 0, which is really same as the surface that we are trying to work with. It's all the same, right? Agreed? Okay. Therefore, because of this equivalence, now we can say gradient of f is perpendicular to the surface that we have. So let's calculate the gradient of f. What would we get?
2x.
Not exactly.
Wait.
Negative, right? Negative
Oh,
2x.
negative.
Negative 2y. If I differentiate by y, it's negative 2y. If I differentiate by z, I get
Minus -1.
negative 1. So we found the gradient. Gradient is just the vector created by taking partial derivatives with respect to x, y, and z. That's all we need. Okay. And then if we evaluate gradient of f at the given point 2, 1, 11, what would that give us? Okay, what do I mean by evaluating at 2, 1, 11? What does that mean? That means for x value, I'm going to plug in 2. For y value, I'm going to plug in 1. And for z value, I'm going to plug in 11. That's what I mean, right? For this given function. So let's calculate that. Negative 2 times what? 2. Negative 2 times 1. And negative 1 times?
Nothing.
Nothing. There's no z here, right? So it's just negative 1. So all I'm doing is the following. Any x should be replaced by 2. Any y should be replaced by 1. Any z should be replaced by 11. But there's no z here, so I don't replace by anything here. Okay, therefore we have the vector negative 4, negative 2, negative 1. And that's, in this picture, it's a vector that's going downwards, right? And it's perpendicular to the plane that we want to find out. We have the normal vector. Now we're going to use it to write down the equation of the plane. How do you write down the equation of the plane now? Well, if you forgot the equation of the plane, it goes like this. A, x minus x naught plus b, y minus y naught plus c, z minus z naught equal to 0. That's the equation of the plane, right?
Yeah.
So if we use that here, it's negative 4 times x minus 2 plus negative 2 y minus 1 plus negative 1 z minus 11 equal to 0. So that's the equation. If you wanted to further simplify this, I would do the following. I would multiply negative 1 so I get rid of the negatives. And then multiply these out so you get 4x minus 8 plus 2y minus 2, z minus 11 equal to 0. And then 4x plus 2y plus z is 21 on the other side. That's the equation of the plane that we have. Okay? So that's how you do the tangent planes. Now, what is this thing then? Normal line. Normal lines are very similar. By normal line, I mean a line that's passing through this given point, and it's perpendicular. It's perpendicular to the tangent plane. Okay. So this is the tangent plane. Let's think about the normal line at where is it? 2, 1, 11. How would you write that? Well, it's going to pass through this point. What's the direction vector? For line equations, we need the direction vector and a point, right? What's the direction vector? Normal means the direction of this line is perpendicular to the surface, so that means we're still using the same vector. Okay? That vector, we know that it's perpendicular to the surface. So we can write down the equation of the line as the following. First, write down that vector, -4, -2, -1, t, 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 and write down the point +2, +1, +11. That's the normal line. Simple, right? So sometimes you would be asked to find the equation of the normal line, in which case you should write down the line equation. Sometimes you would be asked to find the equation of the tangent plane, which would be using this plane equation. Don't ever confuse the two. I've seen people confusing the two and writing down line for questions that require planes and vice versa. In both cases, the important tool for doing that is to define this new function of 3 variables as the function minus z, so that the given surface that you want to work with is represented as a level surface of some 3 variable function. That's the important idea. If you understood that idea, then everything is very easy.